This video is on periodicity. Periodicity will involve an analysis of certain trends in the periodic table, such as trends in ionization energy, electronegativity, atomic radius, as well as a discussion of valence electrons and the properties of different elements. Let's first discuss what periodicity means. It means that there is a repeating pattern in this table. So if you go through, let's say, row number 5 in the periodic table, you will see there's a pattern in the radii, the ionization energy, and electronegativities. When you get to the end of that row and you start again, you'll see a very similar pattern in whichever specific characteristics of the atom you're discussing. All right, so there's this repeating pattern, and because of this, like if you know the idea of periodic law is if you know, let's say, the atomic number, right, of an element, and you know its placement on the table, you already know a lot about that element, what it will do, what type of bonds it might form, what type of physical and chemical characteristics it will have. Now, the first thing we should talk about are valence electrons, which we've seen before, and very briefly, the families of elements. And so let's go through it super fast, okay? I'm not writing it out. Just a reminder, these are alkali metals, these are alkaline earth. These are transition metals, okay? They're lumped together, and that's just the way it is. These A groups are the ones that often get studied. They're the ones that usually used for periodic trends. Continuing though, 7A, these are the halogens, these are the noble gases. These two groups are considered to be the active metals, although aluminum is also considered a very active metal. The halogens are considered to be the active nonmetals, and the noble gases are inert, unreactive gases. They do not react. The transition metals, the only thing you need to know about them is they tend to form colored compounds. And these guys down here are called the inner transition metals. They're often named after the row they're in. So things in the first row are called actinides, and things in the last row, did I get that right? I always forget. No, I didn't. So I'm sorry. These are called lanthanides, and these are called actinides. Sorry about that. I'm not going to erase the whole video over that thing. All right. Valence electrons. So there are core or kernel electrons and valence electrons. Valence electrons are found in the outermost occupied energy levels. So for lithium, whose shell configuration is 2-1, it has one valence electron. And that has a lot to do with its physical and chemical properties. Okay, both lithium and sodium, which are alkali metals, are soft metals. They float in water. They're less dense than water. They're very malleable to the point that, like, if you squish them, it's like playing with Play-Doh. Okay, that's how soft they are. Not lithium so much, but sodium and the other ones in the family. Although lithium can be cut with a knife, like with a butter knife. Okay, sodium is 2-8-1. So everything in this first group here has one valence electrons. Fun fact: hydrogen is not considered an alkali metal, and that's really important. It's a non-metal, so even though it's in the same column and has one valence electron, it's considered, its own little guy who does its own thing. All right. The halogens I've listed here, fluorine is 2-7 and chlorine is 2-8-7. All these guys have 7 valence electrons. The other electrons in here are the core electrons. Now, core electrons generally are not lost, gained, or shared when bonding occurs, but obviously they can be removed if you use a high enough energy photon, which is what we just covered with photoelectron spectroscopy, or when you're doing that, you're using what is termed ionizing radiation. That's high energy, short wavelength types of light, like UV light in the higher energy range. Transition metals valence electrons are a little bit more difficult. I'll do one of them. I'm going to do this guy right over here, and then I'm going to just talk briefly about an exception over here, which you don't know according to the AP, but I think you might want to be at least aware of to explain why it does what it does. All right. In terms of bonding, most of the transition metals have 2 valence electrons, which let me show you why that is. So if you do this one right here that I'm going to fill in right now, okay, its electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d3. If you do it shell notation, it's 2-8-11-2. All right, I think it's 11. I added it really quickly. Now, this is considered the valence electrons. Even though you filled in 3d3 last when you were writing out the configuration, when this element bonds, and it will bond ionically because it's a metal, it will tend to lose 2 electrons. Now the weird thing is these guys do all sorts of things to become stable, and there's no set rule. However, just be aware that it's these electrons here, okay, that probably be the first ones removed. All right. There are a lot, but there are lots of weird exceptions. Like this is vanadium. Vanadium will go +2 and lose those two. It will also go +5, in which it will lose all 3 of its d electrons. So there's no set rule, but you should be aware of the most likely electrons to be lost by these guys are the first 2, the 4s2, for every single element in that row. Now, at the end of the row, when you get to copper over here, you see some weird exceptions. So, copper, when you're at the end of it, you do 3p6, and then the weird thing is you do 4s1, 3d10. Why does it do this? Supposedly, it's more stable this way. So essentially, you don't finish this up, and then you start finishing this, and having this full energy level, sub-level here, makes it more stable. And that's why a lot of the guys in this row column right here have +1 oxidation states. For example, silver only does +1, because it ends in like 6s1 or ends up 5s1, 4d10. I don't think it's important, but I figured I would explain that fact.